start whenever. Just let me know.
Yeah, I'll just introduce you quickly and then you can give you the.
Okay.
Okay, so I think we started recording now. Yeah. Okay.
Yeah, everything right.
Great. Yeah. So thanks everyone for coming to the new edition of the Quantum Spain seminar. Yeah. So today we're very happy to have Andrew Lucas, who works at the University of Colorado at Boulder in the US, and yeah, he's done a lot of very interesting work on quantum many-body physics, very widely, and he has also some focus on mathematically rigorous results. And lately, they've been working on LDPC codes and their properties, which are relevant for quantum information and quantum computation. And I think he's going to tell us about the latest results that they have on the topic. So yeah, please, Andrew, whenever you want.
Okay. Yeah. So thank you for the invitation to present some of my recent work to all of you. So today I'll be talking about low-density parity-check codes as stable phases of quantum matter. This work is done with my amazing PhD student, Chao Yin, funded by the DOE. So I think that our work is a generalization of many older ideas in the literature, connecting, let's say, the theory of error-correcting codes to stable phases of classical and eventually quantum matter. So I'll sort of spend much of the talk just kind of going over this story about the connection between sort of statistical physics, phases of matter, and error-correcting codes. And then hopefully at the end, when I sort of talk about our recent work, it will sort of tie everything together, I hope, in a sort of pleasing way. So yeah, first to just sort of set the stage. So error-correcting codes, right, protect logical bits by encoding them redundantly in some fashion among more physical bits. The simplest example of an error-correcting code would be a classical repetition code, which stores a single logical bit, a 0 or 1, by just repeating it many times. So you can say I have n physical bits in the system, but k equals 1 logical bit. Do I have all zeros or all ones? And we would say that this code has distance d, where d corresponds to essentially the number of discrepancies between any two of our code words. So in this example, all the bits differ, so the code distance is n. If I think about the 0 and 1 here as like the two eigenstates of, let's say, Pauli Z operator, then I can define a logical operator as like a product of Pauli X's, a kind of quantum mechanical language that that exchanges the two code words. And although this is a classical code, let's try to take it seriously as a kind of quantum many-body system and see where that takes us. So if I want to connect this repetition code to a phase of matter, I might notice that the repetition code's code words, these all 0 and all 1 states, are the two degenerate ground states of the one-dimensional Ising model. So here, my Hamiltonian H0 is a sort of trivial Hamiltonian, maybe from the quantum perspective. It's a sum over a bunch of commuting terms, which are themselves just products of Pauli Z's. But nevertheless, let's take it seriously for a moment. So this Hamiltonian is a sum of n-1 parity checks, which are these products Zi, Zi plus 1. And we call them parity checks, right, because they're essentially checking whether the parity of the two bits I and I plus 1 match. So we want the sum to be even, if you like. Now, viewed as a quantum many-body system, this 1D Ising model has a symmetry that is an operator that commutes with H0 and further commutes with all of these parity checks individually. And that's precisely the logical operator that we introduced before. So this product of all of the Pauli X's commutes with each of these parity checks. And this is indeed sort of responsible for this sort of phase of matter that this Hamiltonian encodes. So as mentioned, H naught has two degenerate ground states, the all zero and the all one state. We could say that these kind of spontaneously break the Z2 symmetry generated by this product of all the poly X's. And we recognize this as a sort of ferromagnet, right? So the spins sort of spontaneously decide whether to all be in the zero state or all be in the one state. Okay. So that's a sort of phase of matter that hopefully we're all familiar with. We see it in the world around us. So maybe it's a natural question to ask. Is the ferromagnet really a stable phase of matter? And now I'm really going to consider kind of quantum mechanical effects, as well as maybe this purely classical poly Z Hamiltonian H naught. So let me consider a new Hamiltonian, which is H naught plus some small perturbation. Okay. And I ask whether the ferromagnet remains a stable phase. Will H essentially always describe a ferromagnet? And the answer is no. This ferromagnetic phase is unstable, and it's unstable to essentially a longitudinal magnetic field. So you can imagine taking this potential V, or perturbation V, and taking it to just be the sum over all single site poly Zs. Notice that V does not commute with this logical operator X, which was a symmetry of H naught. So we've broken that Z2 symmetry explicitly. And essentially, this is picking out, let's say, the all zero state as the sort of genuine ground state. When epsilon is order 1 over n, where n is the number of physical bits in the system, this perturbation will essentially bring the first excited state of H naught down to the energy level of the all one state. And for this reason, we're going to think of the ferromagnet as an unstable phase. If you think about, maybe adding further perturbations to this Hamiltonian and thinking about either quantum dynamics or classical dynamics at finite temperature, being in the all one state is metastable. So in some finite time scale, the spins will sort of all flip to zero. Okay. Nevertheless, there are settings where the ferromagnet is a stable phase. So for example, we could consider the following perturbation instead, which does commute with the symmetry operator. And now we find that this transverse field Ising model is in a ferromagnetic phase for this parameter epsilon smaller than 1. Okay, so here we kind of have a whole range of stability, at least along this kind of axis of perturbation V, where ferromagnetism still persists. So you might say, well, okay, that just means that anytime I add a symmetric perturbation, then ferromagnetism is stable, but it's unstable to this kind of symmetry breaking perturbation. Unfortunately, that's also not true. So you can add long-range symmetric perturbations that also cause problems and destabilize this phase. So I think there's a sort of interesting question already for this simple Ising model plus perturbations. Essentially, what really stabilizes this ferromagnetic phase? And is there any relation at all to thinking of the Ising model as the repetition code? These are some questions that we'll give some answers to at the end of the talk. Okay. All right. Before moving on to quantum codes, let me just talk a little bit more about a more general family of classical codes. So we might ask whether we can find sort of other phases of matter that are more complicated than the ferromagnet, that are based on kind of more exotic classical codes, And a natural family of codes to consider from a physics point of view will be low density parity check codes. So we've already sort of seen what parity check means. The word low density here means that all of the parity checks in the system, the checking whether two neighboring bits in the 1D Ising model are the same or not, we want all of these parity checks to only involve sort of order 1 bits. Okay. So if we have this property and each bit is not involved in more than order 1 checks, we'll say we have an LDPC code. There's a kind of abstract way that we can organize our description of this code in terms of this parity check matrix with essentially 0 and 1 entries. And the Hamiltonian for the Ising model, just classically, can be rewritten in this way. It's essentially counting the number of ones in the matrix vector product here between the parity check matrix and any bit string. Okay. Now, in this language, we can sort of restate the facts that we already saw for the Ising model in a simple way. So code words are the right null vectors of this parity check matrix serif H. In this language, one of our code words was always 0, but we could have more code words. We could have maybe k linearly independent right null vectors of H. Then we have 2 to the k ground states. And the code distance is sort of the smallest Hamming weight of one of our non-zero code words. And there's no reason we should stop by choosing this kind of simple repetition code, Hamiltonian or parity check matrix. Why don't we choose a different one and see if we can find more exciting properties? So a more exciting family of codes are these kind of random LDPC codes, where essentially we sort of randomly generate the Tanner graph of the code such that each parity check has delta C bits and each bit is involved in delta B checks. And these codes are rather different from the Ising model. They don't live in finite spatial dimensions in some practical sense. And more interestingly, maybe from the error correcting perspective, they are with very high probability good codes, where the number of logical bits that are stored in the code is proportional to n if you choose the right values of delta B and delta C. But also the code distance is also of order n. So you're storing a lot of information with kind of finite overhead per logical bit, but yet this information is very well protected. It's very difficult to sort of induce an error in these codes. From the physics perspective, these classical codes are just few body interacting Hamiltonians. H naught is a sum over products of z's. They have a larger symmetry group generated by all of the logical code words of the classical code. There was some nice work about a year ago kind of emphasizing some of these connections in physics. And one kind of interesting fact about these codes, which isn't really the point of today's talk, but I'll just highlight because it's interesting, is that these codes kind of can be understood as frustration-free spin glasses in some sense. So, all of the parity checks are simultaneously obeyed on all of the ground states. Nevertheless, this system will exhibit a kind of glassy behavior where if you start, let's say, in one of these code words and you heat up the system, you will stay trapped kind of near that code word. So this code acts as a kind of self-correcting memory from the error correcting point of view. At the same time, you'll find that there's sort of no thermodynamic way to detect let's say the temperature where this self-correction fails. So there's no thermodynamic phase transition at finite temperature in these models, and nevertheless they exhibit ergodicity breaking at low temperature at low but non-zero temperature. So this is kind of already a first clue from the classical viewpoint that maybe these kind of random high-dimensional codes can be very interesting phases of matter. And now let's sort of ask whether the quantum analogs of these codes might also be interesting.
Sorry, quick question. What do you mean here by ergodicity breaking?
Right. So so if we ask about the sort of overall Gibbs ensemble of of this Hamiltonian H naught, you have both 2 to the k different kind of code words that you should explore if you're kind of thermalizing, so to speak. But you also have lots of these kind of glassy, like fake code words that are very deep minima in the energy landscape, but don't correspond to code words. Very few parity checks are violated, but there's giant errors. And so the point is that you kind of explore only an exponentially small fraction of this configuration space, let's say under a kind of metropolis algorithm at low temperature for an exponentially long time, for a time e to the n. So that's ergodicity breaking.
By the way, for the audience, I didn't say it, but if you have questions at any point, you can write them on the chat, and I can relay them to the speaker also. So sorry, please. Yeah.
Okay. Okay. So that's kind of those are some aspects of the phases of matter generated by classical codes. And now we can ask, what is the generalization of this story if we talk about quantum codes? So we can sort of formally just say a few things about what we mean by quantum LDPC code. So for quantum LDPC code, we're taking 2 classical codes, HX and HZ, such that they obey this kind of compatibility condition. And from maybe a more physical perspective, this corresponds to considering Hamiltonian's H naught, which, as before, are the sums over the parity checks of the code. But now we have sort of X and Z type checks. The X checks will be products of poly X's, the Z checks products of poly Z's. The compatibility condition tells us that these X and Z type checks commute, so this is sort of a solvable problem. And as before, we have logical operators that generate symmetries. So we have 2 to the k, degenerate ground states of H naught, and these represent our quantum code words. Again, it will be helpful to sort of get ourselves in the right frame of mind with an example. So this sort of analog of the 1D Ising model for quantum codes would be the 2D surface code or toric code, depending on boundary conditions. So here I've sort of depicted the surface code. We have qubits as black dots here. The orange squares correspond to X-type parity checks, so like an XXXX parity check. And the blue squares are the Z-type parity checks. This code would store a single logical bit of information with the logical X and Z operators depicted here. We could again ask the same question that we did for classical codes. If we take the Hamiltonian H naught and we perturb it by anything, are we in the same phase? Okay. So is the surface code, a stable phase of matter? Is it more or less stable than the ferromagnet that we saw before? Now, this time, we might be more optimistic that the surface code should be a genuinely stable phase of matter. And the reason is the following. From the quantum code perspective, let's ask sort of what it would take to find an operator P which didn't have a vanishing expectation value in any ground state of the code. The operators that can do that will either be the sort of parity checks or the stabilizers of the code themselves, or products thereof, or logicals. And these are these strings that are sort of square root n in length. Now, the Hamiltonian H naught sort of already picks out as ground states all the states that simultaneously satisfy every single parity check or stabilizer. So it seems like the only way that we can sort of lift the degeneracy between our ground states, let's say thinking about doing perturbation theory order by order in epsilon, would be that we have to sort of build a perturbation in V that really forms a logical string. That's sort of the only way we can see splitting this degeneracy of the ground state. But if V is a sort of few body, is a sum of few body terms, whether or not they're geometrically local, this isn't going to happen until very high order in perturbation theory. So we might expect that really the, if we perturb H naught by epsilon V, we essentially protect the degeneracy of the ground state up to, some exponentially small splitting in the system size or in the code distance. Okay. So we might expect that the toric code should really be a stable phase against all perturbations. The difference with the ferromagnet would be that from the quantum code perspective, the repetition code has a good x distance, but a lousy z distance. And in fact, the perturbations that destabilized the ferromagnet were precisely sort of perturbations that looked like the logical z operators of the code. So the fact that we can't do that for the surface code might lead us to suspect that the surface code is an honestly stable phase. And to really sort of make that intuition precise, we would like a diagnostic for what it means to be in the same phase of matter. And slightly informally, the way we try to sort of make this precise is we say that psi1 and psi2, let's say the ground states of H naught and H naught plus epsilon V, will be in the same gapped phase if there's essentially a unitary that connects psi1 to psi2. This unitary should be generated by finite time evolution with a kind of quasi-local Hamiltonian. And we want this unitary to never close the gap between H naught and H naught plus epsilon V. I didn't sort of write down all of those details, but this is the essential idea. Oops. Okay. Maybe more intuitively, you can think that psi1 and psi2 ought to be connected by some finite depth circuit. Maybe for formal reasons, we should expect that you're not really going to be able to do this with a strictly local finite depth circuit for connecting the ground states of two general Hamiltonians. But the idea is that if we sort of allow ourselves to do this and use this Hamiltonian evolution instead, we can probably do the job. We can sort of quibble about exactly how local H should be, but this is essentially the crucial point. And for spatially local perturbations V to the surface code or the toric code, a very nice paper 15 years ago showed that this is indeed the case. So, so we know that against local perturbations, the surface code ground state is really absolutely stable against perturbations. And this is really a robust phase of matter, much more so than the ferromagnet. Okay. I don't want to say too much about how that's proved because I'll sort of sketch the proof of a more general result at the end of the talk. But let me point out one thing that's important, that's a subtlety you might not appreciate sort of from the argument I just gave. So the argument I just gave might suggest that really having a high distance quantum code was what made the toric code a stable phase. But that's not really enough. And we can see that by the following kind of gimmick, where we consider H naught to not be the sum over the toric code's stabilizers, but we really kind of build this Ising-like model where we couple adjacent parity checks on the 2D lattice. And what this does is it gives us two additional ground states on the code. So we not only have the sort of honest code words of our code as ground states of H naught, but we also have some kind of fake code words where if I did this correctly, you put a bunch of kind of Y errors on certain qubits in the lattice. This flips every single parity check. But because H naught, right, is a product of two parity checks, this keeps the value of H naught the same. With this kind of extra degeneracy, this now has the exact same instability as a phase as the ferromagnet. I can just sort of turn on a little perturbation that prefers the true code words over the fake code words, and that splits, that closes the gap of the Hamiltonian, and it ruins my phase of matter. Okay. So in addition to having a good quantum code, we need one other ingredient to make the toric code a stable phase. What is that one extra ingredient? Well, it was, for the surface code, it was found to be what's called a local topological order. So in the surface codes and the toric codes, the stabilizers of the code are essentially loops of poly X's or poly Z's. And each one of those loops you can think of as a product of the sort of fundamental checks in a whole, or sorry, you can sort of fill in, let's say, the loop denoted here in blue with the product of all of the checks in red. These form your stabilizers. Now, the crucial thing is the following. If we were if we were sort of doing perturbation theory and trying to show that, you know, our perturbation V is never splitting the gap between the ground states of the surface code, the way we're going to do that is essentially by showing that, well, if we have a stabilizer, if we have a term in V that sort of acts on the blue qubits here, then all of the operators that it anti-commutes with, sort of all of the dangerous terms that we might develop, these will essentially correspond to things that look like logical operators locally. That's this kind of green string. We may not flip any of the checks along the blue string. We might flip a check inside the blue region. But essentially, there aren't so many of these sort of additional checks that we can violate. So essentially, if we're willing to sort of look at this stabilizer in set S and just expand the set S to a set S bar, which fills in the hole, then we have a kind of local nil-Laflamme condition where projecting onto the local ground states, that's this P S bar, any operator that's, you know, not too large, projected locally into the ground states looks like the identity. So this is really the crucial feature of the toric code that renders it absolutely stable. And this property doesn't hold in the gimmicky example on the previous slide because, of course, the parity check matrix or the parity check operator C would distinguish the sort of left ground state from the right ground state locally. Okay. So now we want to try to sort of merge all of the stories that we've been telling together. So we've been discussing quantum codes, at least those with local topological order, as absolutely stable phases of matter. And we know that classically there are really good codes where the code distance and the number of logical bits stored both scale with the number of physical bits. Quantumly, these good codes have also been discovered in the past few years. As in the classical case, these are kind of not codes that exist in finitely many dimensions, but if we sort of abstract our thinking about many-body physics to just exist in the kind of computer science, you know, k-local sense, these codes are well-posed, you know, Hamiltonian many-body systems. So we might ask whether there is a notion of stability that might extend to these good codes as well. And just like the Ising model is a classical LDPC code, the surface code is also an LDPC code. It's just one that doesn't have, the good scaling above. D is square root n and k is 1. So we might ask whether the stability of the surface code that we've just seen is really kind of a special case of a more general result about the stability of quantum codes more generally as phases of matter. And so that's essentially the question that we have addressed. So at long last, I can sort of state our main results. So the setup is exactly the same that we've been talking about so far. We take a Hamiltonian H, which is the sum of H naught. This is just this, let's say, sum over parity checks for a quantum LDPC code. And we really add any perturbation. I put any in quotes because, it has to be sort of few body, and I'll say a little more precisely conditions later. But morally speaking, any sort of reasonable perturbation V we can add. And we show that if this code has something called check soundness, which I'll define on the next slide, then the ground state degeneracy of this Hamiltonian H is in some sense robust, so long as the code distance is at least logarithmic in the number of qubits. And what do I mean by robust? Well, like for the surface code, the exact degeneracy is not robust. However, the gap between, let's say, 2 to the k ground states of H naught and the 2 to the k lowest line energy levels of H naught plus V will stay constant, essentially, as we kind of adiabatically deform from one Hamiltonian to the other. The energy splitting between these ground states will be exponentially small, morally speaking, in the code distance D. So that looks just like what we saw for the surface code. And there's this quasi-adiabatic unitary U that rotates me between the two sectors, the two sets of ground states. So in this sense, we have a stable phase of matter, an absolutely stable phase, just like for the surface code. So that's kind of the main result. I should acknowledge some related work by other authors. So in May of last year, this first group of authors proved a sort of weaker result for codes that didn't live on expander graphs, but nevertheless sort of extended the known stability of the surface code. And that sort of inspired us to try and sort of close the conceptual gap and to study good codes as well. And then contemporaneous to us, there's another paper by de Rooij et al. That does something a little bit different, but kind of morally their conclusions are very similar. So, okay. If there's like one pop sci takeaway, like what makes this result very surprising, notice that up here, right, we have a code H naught, which has a curious property. It has an extensively degenerate ground state when the number of logical bits k is proportional to n. And that implies that H naught has a constant entropy density at 0 temperature, which is a violation of the third law of thermodynamics. Now, you might expect that that's a kind of accident of this finely tuned Hamiltonian. Maybe when I perturb this Hamiltonian, the degeneracy splits in such a way that the entropy density would vanish as I approach 0 temperature. But we see from this argument that actually the entropy density is really finite until you get maybe to temperatures that are like e to the minus n. But that's kind of ridiculous. That's unphysical. And so for all practical purposes, these codes really form stable phases, all of which violate the third law of thermodynamics. So in this sense, we sort of have to rewrite our sort of understanding of statistical physics. And I think that's quite exciting. Okay. What is check soundness? What is the property that we need to prove this stability? You might expect that it's going to be something like local topological order. But local topological order to us kind of felt like it had a very geometric intuition in 2, 3, etc. spatial dimensions. So check soundness is in some sense an abstraction that we can state for any code. So let's take Hamiltonian H naught. It's a sum of commuting stabilizers. And we'll say that this Hamiltonian has check soundness if any stabilizer that acts on a small number of qubits, let's say m less than the code distance d, can be written as the product of some of these generators in the Hamiltonian, where this product should be small. Okay. So if we have, m is order 1, then there's an order 1 product of kind of fundamental stabilizer generators that builds S. More precisely, we want the number of stabilizers we need to scale polynomially with m. And our proof will require, in general, that this parameter a is smaller than 2, or if the code can be embedded in finite spatial dimensions, any finite a is fine. Happily, sort of all of the popular quantum LDPC codes have check soundness with parameter a equals 1, so they're well within our stability bounds. Okay. All right. And just to kind of connect for a moment with what we had said earlier about local topological order, what is check soundness saying? Well, in this language, check soundness is the fact that any loop, in blue here S, if you fill in the loop with products of the fundamental checks, right? Since area is sort of always less than or equal to perimeter squared, roughly speaking, we can always sort of fill in the blue loop with at most sort of perimeter squared fundamental checks, and that's check soundness. Okay. Now, one thing that I might have sort of glossed over briefly in stating the main result, but let me highlight at this point, is that our definition of check soundness and our criterion on the V for which we can prove stability does not require that the perturbation is local with respect to the interaction graph of the code itself. So our theorem proves the stability of the surface code to sort of k-local, but spatially non-local perturbations. And as far as we can tell, that's a new result about the stability of this phase. So we sort of know that the surface code is an even more stable phase than was known before. Okay, let me just spend a couple minutes trying to sketch how one tries to prove a result like this. So, okay, for technical reasons on the slides that follows, I'm just going to sort of shift the ground state energy of the Hamiltonian so that it's 0. And the restrictions on this perturbation V are essentially that V is a sum of operators, but the more sort of qubits each operator acts on, kind of the exponentially smaller the coefficient of that term is. So I want a kind of exponential in volume suppression on the size of each operator. Now what I'm going to do is try to explicitly build this quasi-adiabatic U that rotates me from H0 to H0 plus epsilon V, or maybe better to think of going the other way. So given H0 plus epsilon V, I'm going to try to build a U1 that essentially takes me to H0. There will be some order epsilon errors, but I want them to sort of not act on the ground state. I want them only to kind of be on excited states. It can act as the identity on the ground states, but it might do something non-trivial on excited states. And then I want the perturbation to be epsilon squared. So I'm trying to essentially do perturbation theory. However, I'm doing perturbation theory on operators, not on states. This goes by the name of Schrieffer-Wolff transformations. And our goal is to implement this kind of rotation while preserving the locality of things like D2, V2, and then the higher order dk and dk. And we can iterate this procedure very carefully up to extremely high order, in fact, of order the code distance. And just a sort of brief technical remark here, in many of the previous proofs of stability, one relies at this point on what are called Lieb-Robinson bounds. Lieb-Robinson bounds essentially tell you that if you time evolve operators, they kind of grow with a finite velocity on the interaction graph. However, on an expander graph, this means operators grow exponentially fast, and that's really bad for the convergence of this series. So we instead use kind of cluster expansion techniques instead. And sort of importantly, the more parity checks that we violate as we grow bigger and bigger operators, kind of the weaker the rotation that U needs to apply to kind of undo the perturbation. And that's a sort of useful trick for us. OK, check soundness enters the proof in two places. First, it just helps to control the locality of the operators in this Schrieffer-Wolff transformation. And also, check soundness is important to verify that the D that we build really doesn't kind of lower excited states into the ground state energy band. So we know from the arguments that we've given that D will not split the degeneracy of our ground states, but we need to also check that we don't kind of lower the energy of an excited state below one of the ground states, and check soundness is sort of important for that. OK. Having established this sort of quantum result, there are some kind of nice generalizations to classical codes as well. So firstly, if we have a classical code Hamiltonian H0, if that code is check sound, then it is stable in the same sense as the quantum code to all symmetric perturbations. Now, the Ising model was not check sound, and that was why we saw that certain long-range symmetric perturbations could destabilize the Ising model, even though these long-range perturbations were few-body. And what does it take basically to get stability for Ising H0? Well, you need the sort of V to be spatially local. And yeah, I think this is sort of a known result, but we can sort of see it as an immediate corollary of this more general result as well. There is something new, though, in this last corollary, which is that we constructed this quasi-adiabatic U, but our locality bounds on U are kind of volume law rather than sort of diameter law. So when you derive U based on or bound U based on the Lieb-Robinson bound, basically you know that terms in U that act on a ball of radius r are suppressed as e to the minus r. But now in d dimensions, we actually know that this is suppressed as e to the minus r to the d. And this suggests sort of much more powerful properties of U than we had known before. And this is some work that will hopefully appear rather soon. Just to give sort of an example of what we're doing, so let's take this ferromagnetic phase that we started the talk with. If this U has these exponential in volume tails, then we show that the expectation value of what's called the disorder operator, this corresponds to essentially taking the symmetry operator, which was the product of all poly x's, but just restricting it now to some region of size r. We can take this disorder operator, and we can show that its expectation value in the ferromagnetic state would be exponentially small in volume. sorry, the notation here might be a bit awkward. R is set, not radius. Said set. Okay. This is interesting because there are states that appear to be ferromagnetic, but violate this criterion. These are known as Roxar-Kivelson states. And so I would say we have at least a very strong inkling based on these results that this RK state has to be in a distinct phase of matter than the ferromagnet, even though from the point of view of condensed matter physics, they might seem to be in the same phase. They exhibit the same sort of spontaneous symmetry breaking pattern, but upon closer inspection, the disorder operator in the RK state is sort of not suppressed enough. And these are the kinds of results that we hope to leverage using our stronger bounds on U. So with that, let me sort of wrap up. So I've told you a story today about kind of understanding the robustness of error correcting codes to perturbations from the vantage point of maybe condensed matter physics and of phases of matter. So quantum LDPC codes, sort of in infinite dimensions, define new phases of matter which are absolutely stable against all perturbations and seem to have some very interesting properties. So as I've already showed you, they have this finite entropy density, even as we approach zero temperature, violating the third law of thermodynamics. And these quantum codes also exhibit the same kind of glassy dynamics, quantum memory, as the classical counterparts. So this kind of can make them appealing from the point of view of building kind of autonomous or passive quantum error correcting codes. I think that some of the techniques that we've described, building these kind of extremely local adiabatic generators, may have very interesting applications in condensed matter physics. But I also think it may be interesting to ask whether check soundness is a sort of intriguing property for thinking about the design of quantum codes in its own right. We certainly know that check soundness will guarantee the stability of the code to, let's say, Hamiltonian perturbations, but whether or not it implies additional useful properties from an error correcting vantage point, I think remains to be understood. So that's all I wanted to say. Thank you for your attention.
Great. So yeah, thanks very much, Andrew, for the great talk and the great results as well. Yeah. So if people want to write questions, please feel free to write them in the chat, which I think should be open, and I will relay them to the speaker. But maybe I can start because I have a couple actually. So I guess something intriguing about the results is this thing you mentioned about the third law of thermodynamics. But is there something quantum going on here? Or is this something that was maybe already a property of LDPC codes and just people didn't realize? Or
so I think classically the problem is that the classical codes have the same instability as the ferromagnet. So you can imagine like picking one of the classical code words, you turn on a transverse field or a longitudinal field that kind of prefers that code word, and you immediately restore the third law.
Right.
So it is, I think, a uniquely quantum effect here.
Okay, so the stability. Okay, that's very interesting. Mm-hmm. So I mean, does it have to do in a sense with topological order? Although here there's not really thing, or
I think so. Okay, these other authors kind of, I think they do something somewhat similar to check sound. Like they kind of, I think from their perspective, they just say that this is the generalization of local topological order to kind of generic code. Yeah, so it might, maybe you can sort of say the check soundness is local topological order, I think. Yeah, we wanted to give it a new name, but it's, yeah, maybe it's not really so different.
Yeah. And maybe a bit more of a technical question. You mentioned you use the cluster expansions for these models. Is this just having to do with the growth of nested commutators, or is it something else?
Yeah. So okay.
Maybe this.
So if I go back to this point, yeah. So I think the way I would think about it is that because this epsilon is small, we sort of know that at each step of the rotation, right? So we're sort of rotating by a small enough amount that we might expect the cluster expansions to converge fairly efficiently. And the crucial thing is that the cluster expansion kind of protects this volume law suppression,
Yes.
and that's something that we can confirm. And I think, yeah, with Lieb-Robinson bounds kind of as they stand, that that we know how to do. Yeah, I think maybe one other aspect which I think of as kind of important in this discussion is that so actually the first place where we had sort of developed similar techniques was in trying to understand basically the quantum decay time of the false vacuum in the Eisen model. So, in the presence of this longitudinal field, you look at the state with all ones, you ask kind of how long does it take for, let's say, quantum fluctuations to kind of kick me out of this false vacuum. And in higher dimensions, we have this intuition that it actually gets harder because you have to nucleate a bubble, right, to go from the sort of false to the true vacuum. But the kind of off resonance, the energy cost of that domain wall is growing sort of the bigger the bubble gets. And Lieb-Robinson bounds, we found, seem to not really capture that physics. And this approach does. So this denominator here is in that context allows us to sort of capture the fact that larger perturbations are sort of more and more off resonance, so that we can sort of kind of make the series converge faster. And that's, I think, the same physics that's going here.
Okay, I think there are two more questions. First, maybe I read the one in the chat first. So the question from Gerard is whether this stability result is related to the NLTS property, so the no low energy trivial states. By Hastings.
So that's a great question. So our results apply for the NLTS code family, but they also apply to hypergraph product codes, which are not known to obey NLTS. I suspect that there is a relation, but the precise nature of that maybe is not known because NLTS may be broader than we know thus far.
Yep.
So.
I think Javier Mas has the hand raised, so I don't know if you can ask the question. Yeah.
Hello, Andy. So I'm Javier. I want to start by thanking you for contributing to this series. So unfortunately, I couldn't arrive in time, but I asked Alvaro, and he gently agreed to chair the seminar. So thank you very much. So I'm not a specialist at all in this business, but I know of a Hamiltonian which has zero temperature entropy, which is this called SYK model, this Sachdev-Yekitaev model, for which there's even a bosonic version. I don't know if you have thought about if there is an LDPC, low density parity formulation of this Hamiltonian or not.
So yeah, so I think there is some work, I don't know it that well, that I think tries to argue that the SYK model is a kind of approximate good quantum code. I probably shouldn't say too much about details because I don't know them, but that is a connection people have tentatively explored. I think there's some work by Brian Swingle on this.
Yeah.
The other thing is I don't know for the SYK model whether this kind of absolute stability of that entropy density is there. For example, if I take maybe the fermionic 4-body SYK model and I add a sort of 2-body fermionic perturbation, does that?
I know, you're right. It immediately gets gapped. Yeah, no, you're right. It immediately gets gapped. That's not pretty stable. Yeah. Okay, so then that might be the answer. Yeah. So thank you very much.
Thanks.
Are there any other questions, either chat or words? Yeah. Okay, that seems not to be the case. Yeah, so I think we can maybe conclude here. Yeah, so thanks a lot, Andrew, for the nice talk and for the results, and for doing a presentation in this series, like Javier was saying. Yeah, so thanks a lot, and thanks everyone for coming.
Thank you very much. Thank you.
Thanks, Andy. Goodbye.
Bye.